27 million people in California depend on a single water system. It feeds cities from the Bay Area to San Diego. It irrigates 750,000 acres of farmland, and it underwrites a regional economy worth $2.3 trillion a year. The system works. It has worked for decades. But the land it runs through is unstable, and the infrastructure that holds it together was never built to last. The Sacramento-San Joaquin Delta sits at the center of this network. It is where fresh water flowing south from the Sacramento River meets tidal influence pushing inland from San Francisco Bay. The Delta is not a single river or a single channel. It is a sprawling maze of waterways, islands, and reclaimed farmland, threaded together by a system of channels that route fresh water toward the pumps that send it south. Without the Delta functioning as a controlled freshwater corridor, the aqueducts that serve Southern California and the Central Valley have nothing to carry. Holding that corridor in place are 1,100 miles of levees. Many of them were constructed more than a century ago, not by engineers, but by farmers and laborers working to reclaim marshland for agriculture. The material was what was available: uncompacted soil, placed on top of soft peat that had accumulated over thousands of years. These were farming levees. They were built to keep fields dry, not to serve as the structural backbone of a statewide water delivery system. But that is exactly what they have become. And the peat beneath them continues to decompose and subside, lowering the islands they protect and increasing the pressure on levee walls that were marginal to begin with. The seismic risk in this region is not theoretical. Current probability models place a 72% chance of a magnitude 6.7 or greater earthquake striking the Bay Area by 2043. That is not a worst-case scenario. It is a baseline expectation. A quake of that size, centered near or beneath the Delta, would not need to destroy every levee. It would only need to breach enough of them in the right locations. If multiple levees fail simultaneously, the geometry of the Delta turns against itself. Saltwater from San Francisco Bay would push inland through the broken channels, driven by tidal pressure into the freshwater zones where the pumps draw their supply. That intrusion would contaminate the source water, not with sediment or debris, but with salt. And salt cannot be filtered out at the intake. It has to be flushed through the entire system before deliveries can resume. Engineers have modeled what that recovery looks like. The answer is a 20 to 30-month interruption in water deliveries. During that period, the levees would need to be rebuilt, the salt water pushed back out by controlled freshwater releases, and the channels tested and cleared before the pumps could restart. 2.5 years at minimum, with no water moving through the primary supply corridor. That is not a drought. It is not a shortage that can be managed by rationing or conservation. It is a full stoppage of supply for more than 2 years to a population larger than the entire state of Texas. Farms would go fallow. Cities would scramble for alternatives that do not currently exist at scale. The economic damage would reach into every sector the water system touches, and it touches nearly all of them. This is the problem the Delta Conveyance Project is designed to address. Not to replace the existing system, but to build a second path. A backup route that can move water south even if the levees fail. The idea is not new. Its roots stretch back more than 80 years. The earliest version of this concept was the peripheral canal, first proposed in the 1940s as an open channel that would carry Sacramento River water around the eastern edge of the Delta, bypassing the fragile interior waterways entirely. That project moved through decades of study, engineering revisions, legislative action, and public debate. It reached the ballot in 1982, and California voters rejected it. The reasons were complex: cost concerns, environmental opposition, and deep regional distrust between the water exporters in the South and the communities in the Delta who feared losing control of their local supply. But the underlying problem did not change with the vote. The levees kept aging, the seismic models kept sharpening, and the population, depending on the system, kept growing. The concept returned in 2015 under a new name, California Water Fix, which proposed a pair of large tunnels running beneath the Delta. That design, known as the Twin Tunnels, would have carried 9,000 cubic feet per second of water through 2 parallel bores. It was an ambitious plan, and it attracted both support and fierce opposition. By 2019, it too was shelved. What replaced it is the current Delta Conveyance Project, sometimes called the DCP. It uses what planners refer to as the Bethany Reservoir Alignment, a route that starts in the North Delta and ends at existing infrastructure near the California Aqueduct. The twin tunnel design has been reduced to a single tunnel. The capacity has been scaled down to 6,000 cubic feet per second. The project is smaller than what came before it, but it is still one of the largest tunnel boring operations ever proposed in North America. And the core logic has not changed in 80 years. Find a way to move water around the delta without depending on levees that cannot be trusted. The system begins at the northern end, where 2 intake facilities would be built along the Sacramento River, near the communities of Hood and Cortland. These are designated Intake B and Intake C. Each intake is designed to pull water from the river while preventing fish from being drawn into the system. That requirement shapes everything about how the intakes are built. Each facility uses cylindrical T-fish screens, large curved screening structures that sit in the river flow. Each screen offers roughly 15,000 square feet of surface area. The slots in those screens are just 1.75 millimeters wide. That measurement is set specifically to protect endangered species, delta smelt and juvenile Chinook salmon, from being pulled through or pinned against the intake structure. The screens must be large enough to handle high-volume water diversion, while keeping those slots narrow enough to exclude small-bodied fish. It is a precision problem at an industrial scale. Construction of these intakes is itself constrained by biology. All in-water work is limited to a 3-month window running from August 1st to either October 31st or November 30th, depending on conditions. That window exists to avoid the migration periods of protected fish species. Every year of construction at the intake sites must fit its river work inside that narrow season, and any delays push the schedule by a full 12 months. From the intakes, water enters the tunnel. This is the central piece of engineering in the project. A single deep-bore tunnel stretching 45 miles beneath the delta. The internal diameter is 36 feet. At that scale, it would comfortably fit a 3-lane highway inside the bore. The tunnel would be excavated by tunnel boring machines operating at depths between 100 and 150 feet below the surface. The lining of the tunnel is made from precast concrete segments, each 18 inches thick. These segments are manufactured on the surface, transported underground, and assembled into rings by the TBM's erector arm as the machine advances. Each completed ring weighs more than 82 tons. The rings are locked together with bolts and sealed with gaskets to form a continuous watertight tube. That tube must withstand forces from both directions. From the inside, pressurized water pushes outward against the lining. From the outside, the weight of the surrounding earth pushes inward. At depths between 100 and 150 feet, the geology is not uniform. The bore passes through layers of clay, sand, and silt, each with different densities and different behaviors under load. Clay can swell when wet and shrink when dry. Sand transmits water pressure more readily. Silt sits between the two, unpredictable under stress. The segments must be manufactured to tight tolerances and installed without gaps that could allow groundwater to migrate into the tunnel or allow soil to shift into voids around the lining. Even minor imperfections in ring alignment, compounded over 45 miles, can create structural problems that are difficult and expensive to repair once the bore is complete. The tunnel's depth is not just a matter of avoiding surface disruption, it is also a seismic decision. One active fault, the West Tracy Fault, crosses the tunnel alignment near Byron. Running a canal or pipeline across an active fault at the surface would expose it directly to ground rupture. At depth, the dynamics change. Ground motion at 100 to 150 feet is reduced compared to surface level shaking. The tunnel structure itself can flex within the surrounding soil, rather than being torn apart by lateral displacement. Where the tunnel crosses the West Tracy Fault, the design calls for additional hardening. That includes the use of high-strength concrete, heavier steel reinforcement, and potentially continuous steel rods embedded in the tunnel lining. These measures are intended to allow the tunnel to absorb fault displacement without losing structural integrity. The goal is not to prevent movement, it is to survive it. At the southern end of the tunnel, the water must be lifted. The tunnel runs more than 100 feet below the surface, and the California Aqueduct sits at ground level. Bridging that vertical gap requires a major pumping facility, the Bethany Complex. This is where the tunnel ends and the existing delivery network begins. The complex includes a surge basin, which is the first structure the water encounters after leaving the tunnel bore. At the center of the basin sits a reception shaft with a diameter of 120 feet, reaching down to an elevation of negative 169.18 feet. That shaft is not simply a holding tank or a transition chamber. It is an energy management system designed to handle one of the most dangerous conditions in large-scale water conveyance: hydraulic surge. When the pumping plant is running at full capacity, water moves through the tunnel at speed. If the pumps shut down suddenly, whether by planned shutdown, equipment failure, or power loss, the water in the tunnel does not stop. 45 miles of water in a 36-foot diameter bore carries enormous momentum. That momentum converts into a pressure wave that travels backward through the system. If that wave hits fixed infrastructure without being absorbed, it can crack joints, damage pump housings, or fracture the tunnel lining itself. The phenomenon is known as water hammer, and at this scale, it is a destructive force. To manage it, the surge basin includes a circular weir wall with a diameter of 180 feet. That wall is designed to capture the arriving pressure wave and allow the energy to spread across a broad, controlled surface, rather than concentrating against rigid structures. The water rises against the weir, dissipates its energy, and settles. Only then does the pumping plant lift the water from the basin to the elevation of the California Aqueduct, where it enters the existing distribution network and continues its journey south. Building all of this will take between 13 and 14 years. At peak activity, the project would employ more than 5,000 workers across multiple construction fronts. The intake sites in the north, the tunnel launch and retrieval shafts, the segment manufacturing facilities, and the Bethany complex in the south. The logistics of moving material and equipment to and from these sites are immense. Current estimates place the total number of heavy truck trips at more than 200,000 over the life of the project. Those trips would be concentrated on local roads and Interstate 5, passing through small Delta communities that were not built to absorb that kind of traffic. The communities near the intake sites and along the tunnel alignment would experience years of construction activity, truck traffic, heavy equipment noise, dust, and land disturbance on a scale that does not end in months, but stretches across more than a decade. A community benefits fund of $200 million has been established to offset some of those impacts. The money is directed at the Delta communities most affected by construction. Whether that figure proves sufficient over a 13-year construction period is a question those communities themselves will answer over time. The project carries a price tag of $20.1 billion, expressed in real 2023 undiscounted terms. That figure makes it one of the most expensive water infrastructure projects in American history. It is not funded by the California General Fund or by federal appropriation. Instead, 18 public water agencies, the entities that would receive water through the completed system, are financing the project directly. The cost is theirs, and by extension, it belongs to the ratepayers those agencies serve. Every household and business drawing water from a participating agency would bear a share of the construction cost through their monthly bills, spread over decades of bond repayment. Against that $20.1 billion figure, planners have placed a benefit estimate of $37.96 billion, producing a benefit-cost ratio of 2.2. That calculation factors in the value of water supply reliability, the avoided economic losses from a major seismic disruption, and the long-term protection of communities and industries that depend on uninterrupted delivery. It is a projection built on assumptions. Assumptions about the timing and severity of future earthquakes, the pace of climate-driven water supply loss, the operational performance of a tunnel that has not yet been bored, and the continued growth of the population it would serve. The ratio says the investment is worth making. Whether the future confirms that judgment depends on variables no model can fully control. The regulatory path to construction has already cleared several of its largest hurdles. The final environmental impact report was certified, and the project was formally approved in December 2023. In February 2025, the California Department of Fish and Wildlife issued the project's incidental take permit, the authorization that governs how much impact the project may have on protected species during construction and operation. Additional permits and legal challenges remain, but the procedural foundation is in place. If construction proceeds on its current timeline, the tunnel would be operational by the end of 2044 or the beginning of 2045. That date sits just 2 years past the 2043 window, in which seismologists have placed their 72% earthquake probability estimate. The margin between the threat and the solution is narrow. The tunnel cannot protect against an earthquake that arrives before it is finished. The 1,100 miles of delta levees will remain in place regardless. They will continue to channel water, hold back tides, and protect farmland. The tunnel does not replace them. It runs beneath them, a parallel system buried in the earth, waiting to carry water if the surface system fails. Whether California finishes it in time is a question that depends on funding, permits, geology, and years of uninterrupted construction. The answer is still decades away.